All right, welcome back to class, everyone. Hope you had a really good 2 weeks off. I just to let you guys know that next week there is no class because spring break. Even though it's supposed to be spring break right now, but decided to have class today because it is what it is. But you guys have the week off for next week, and we come back in 2 weeks after this. So you guys get another 2 weeks break, which is nice. But yeah, let's get started on today's topic. So what are we learning today? Learning about something interesting, something you probably won't be seeing in math contests. We're gonna look at some logic. Nope, there's Cheng Loan. And I believe we're just missing one person. Okay. So today we're gonna look at this topic, logic. So what is this about though? Let's look into it. So let's look at something called propositions. So what is a proposition? A proposition is basically, so this is the definition, a statement or collection of statements that can either be true or false. So either one of these, but it can't be both or neither of them. So that's what a proposition is. And propositional logic, so just like a branch of logic in general, and this just means the study of propositions. Very straightforward. And below, I've listed some examples of what are propositions and what are not propositions. So let's look at each one of them, see why it's a proposition or not. So let's look at these 3 examples. So first one is the sky is clear today. So remember, a proposition can either be true or false. And it looks like the sky is pretty clear today. So I'd say this proposition is true. This proposition here, the sky is clear today, is definitely true. Let's look at the second one, the second proposition right here. I'm older than all of you. Hopefully none of you are older than me in this class, but yeah, this is also a true proposition. So yeah, because it is basically a fact, so we can say. And then this final point right here, this is the third slide. This is the third slide in the presentation. So as you can see, this is the second slide in the presentation actually. So this is the first slide, the title page, and then this proposition slide is actually the second slide. So the statement is false, but it's still a proposition, even though it's false. Right. So those are some examples of actual propositions. Now what about some things that are not propositions? So let's look at the first one. So this is asking, what is 1 plus 1? So if you're asking a question, that is not a proposition. So if you just see a question mark, that means automatically it's not a proposition. So, and then the second point, I am the dumbest person in this Google Meet. So this is you can't really determine if this is true or false because it's opinionated. It's kind of opinionated, like being smart at something. There has to be many different factors to consider who's smarter than this person or not. So this statement right here is very opinionated, and there's not really a definite answer if it's true or false. So that means this is not a proposition. So any statement that's opinionated or biased cannot be true or false. So sorry, it's not a proposition. So, and then this final one. So this is an equation. So you have x plus 4 is equal to 10. So the reason why this is not a proposition is because you don't know what the value of x is. Well, you can solve for it, but you don't know, just by looking at this equation without solving it, you don't know what the value of x is exactly, right? You have to solve for it, you have to move forward to the other side. But if you don't do that, then you're not sure what x is. It's a variable, right? It can be any value. So that's why this is not a proposition. So if you don't know if this is a true or you can't really tell if this is a true or false statement, right? So it's not a proposition. Any questions about this slide? These are principal. Xi Lao Sha. Okay. Any questions about this slide? Oh yeah, there's also a chart right here. It's basically, so you see some symbols right here and some definitions. So don't worry about this for now. We'll cover some of these in the later slide, but not all of these. Just some of the more important ones. So you can see terms like assertion, negation, conjunction. You might see some of those, but we'll look at them in later slides. So don't worry about this chart. just to give you an idea of like what propositional logic is like. But hopefully you don't have any questions. Let's move on. So let's look at something called logical connectives. So what I described in this chart, so you see these symbols right here. You see like this small dash, you have an upside down V, you also have a normal V, you have arrows as well. These are what are called logical connectives, but let's look at the definition in more detail. So what is exactly a logical connective? Logical connective is basically a symbol, so remember it's a symbol, is used to connect multiple propositions together, usually. We'll look at some examples of that later, so you get a better understanding of what this term means. But the first logical connective we're going to look at is the knot. It's not really called knot. There's like a more mathematical term for it, but usually people just call it the knot connective. And then it's this symbol right here. It kind of looks like an L that's been rotated or something. So you see this symbol right here in front of the P, and P is basically a propositional variable. So P can just represent like a proposition. P is any proposition you can think of. And the way you read this is not P. So if you see a knot in front of the proposition, then you can use this symbol right here. So not P. So not P right here, this will return true if P is false. So basically what this not does is like it just basically reverses. If it's true, it'll reverse it to false. And if P was false, then it'll reverse it to true. That's basically what the not connective does. Fairly straightforward. And then the more formal name for it is called logical negation. So this bolded term right here, logical negation is the term for this symbol right here. All right. Are there any questions about this before we move on? Okay, if there are no questions, let's move on to the next slide. Okay, we're going to look at some other logical connectives. So we have one called and one called or. So you probably heard them very often in like normal day English language, but like what do these terms actually mean in like mathematical language? Let's take a look. So for the and connective, this is the symbol. It's basically an upside down V. And here you have two propositional variables. You have P and you have Q. So they can either represent true or false propositions. So you have P proposition and a Q proposition. And in between you have that and connective, which is the upside down V symbol. So this is read as P and Q. So if you see the and symbol, if you see and inside like a proposition, that means you know that there's a symbol. So P and Q is true. So this compound proposition, so sometimes we call this a compound proposition, is like when we combine two propositions together. So this P and Q returns true if both P and Q are true. So these both have to be true if you want this entire thing to be true. If one of them becomes false, then the entire thing will be false. Right? And then the more formal name for this connective is called logical conjunction. So this bold term right here, logical conjunction, that's what this represents. All right, so that's the logical conjunction connective. Now let's look at the next one. So this is or. You see, it's a very similar symbol, except it's not upside down. It's a normal V. So you have P, V, Q. Well, but you read this as P or Q. So if you see or in a proposition, that means you know that you have this V. So P or Q is true if either one of P or Q is true. If any of them are true, if any of P or Q is true, that means this whole thing will return true. So like if you say you have P is true, even though Q is false, this will still return true. And if they're both true, it will obviously still return true as well. And then our name for this is called the logical disjunction. So you see, and was called conjunction, or is called disjunction. It's slightly different. Right? Are there any questions about this slide? Any questions? Okay, if there are no questions, let's move on. Okay, let's look at something called truth tables. What are truth tables? So you can see that, so there are these three tables right here. You can see that there's like these, like for the headings, you have the propositional variables. So you have P. Some of them also have another column for Q. So some of them have 1. So this one, remember, this symbol represents the, it was a not connective. It was called logical negation. So this is a logical negation of P. And we've seen this one. So this is the upside down V, which represents the and. So you see right here. It's called logical conjunction. And you see for this table, we have this heading for logical disjunction, which is the or. So you see it's just a normal V. Oh, someone's joining. Oh, now we have full attendance. Nice. So you can see for each of these tables, we have the propositional variables and then the compound propositions. So you see there's not P, there's P and Q, and then P or Q. But like, what are truth tables? What do they do? So in truth tables, we want to find out all of the possible values of not P. So basically the proposition that we're trying to solve for. So not P is this case. In this case is P and Q. In this case is P or Q. So what truth tables allow us to do is to find out all the different possibilities of true or false results for these propositions based on all the possible like combinations of just P or P and Q together. So you can see for this left table right here, there's only 2 possible values for P that you can have. You can have false for P, or you have true for P. So remember that P is a propositional variable, is a proposition. And then basically not P, basically you're just flipping around these signs. So you're basically changing false to true, and you're changing true to false. So those are the possible results of not P. So in the middle, and then in this middle table right here, so this is P and Q. So remember, for P and Q to be true, both P and Q have to be true. So you can see right here, P is true, Q is true, then P and Q returns true. And then you can see for all the other cases, so you have 2 falses. You have P is equal to false, Q is true, or you have P is true and Q is false. And these will all return false for P and Q. So that's a P and Q table. And then this final table is P or Q. So remember that for P or Q, either one of P or Q can be true, and that will return true for P or Q. So you see that for false, so P is false, Q is true, P is true, Q is false, or P and Q are both true, these will return true for P or Q. Right? And if they're both false, then obviously P or Q is going to return false. So that's what a truth table does. Basically returns like all possible values of P, basically all the possible values of a proposition based on all the possible combinations of the propositional variables, which are P or Q, or whatever. You can name them whatever you want. But are there any questions about this? Any questions about truth tables? This table reminds me of Coincide, except heads is face. Yeah, there's a lot of like, oh. Yeah. Sorry, technical issues with my headset. Yeah, this is very relatable to like probability tables and stuff. Trying to map out like all possible outcomes. Yeah, that happens fortunately. Okay, are any questions about this slide there? Next slide, we have a couple of problems, so hope you guys are prepared. Actually, they're very straightforward. Let's go to the problems. So here are the problems. Let P, so P is a propositional variable. So say P represents the proposition that it is snowing outside in Waterloo right now. And Q, so another propositional variable called Q, is equal to France is in Europe. Determine if each of the following propositions, so each of these, determine each of them are true or false. Right? Using your knowledge of the connectives, what they mean. I'll give you guys 1 minute or so to figure these out. Yeah, first determine if P and Q, so determine if each of these are true or false first. Remember to do that. Wait a couple more seconds. Hopefully most of you are finished. Elaine got all the answers. True, true, false, true. Okay, so let's take it up. So for the first question, we have not P. So you see this symbol means not, so logical negation, that's what it's called. You don't have to memorize like what these terms actually are. You can just call this like not, well, you just call them not and or, that's fine. But yeah, so this just represents not P, so the opposite of P. So you see that P, this propositional variable, it says it's snowing outside in Waterloo right now. If you look out your window, hopefully you have a window in your room, but if you see out your window, you can obviously tell it's not snowing, right? It's very sunny outside. So this statement is, this proposition is obviously false. P by itself, that is. But if you take not P, so if you reverse the false, that means you get true. This thing will return true if P is false. So if P is false, this will return true. So that means answer for question number 1 is true. Yeah. Oh, you're outside right now, Aiden. You're listening to this outside. That's interesting. All right. Yeah, so hopefully you can tell the weather outside is very nice. So question 1 is true. Now let's look at question 2. So this is PVQ, so this is normal V. This is, it's called logical disjunction, but you can just call it or. So this is P or Q. So remember, normal V represents or, and upside down V represents and. So it says P or Q. So you see P is false, right? It's not snowing outside Waterloo. What about Q? Q says France is in Europe. So France is obvious. France is a country in Europe. Hopefully you guys know that. So it means that the proposition Q is true. So you have P is false, Q is true. So false or true, that means that will return true. If you take a look at our truth table, yeah, you can reference these truth tables because these are very useful. So you see false, so P is false, Q is true, this will return true. So it means question 2 is true. Okay, what about question 3? So this is P and Q. So remember, P is false, Q is true. Remember, for P and Q to return true, both of them have to be true. So if P is false, that means this whole thing will return false. And if you we can verify that. So you see that P is false right here, Q is true right here. So this second line, you see that P and Q returns false. So question 3, answer is false. What about question 4? So question 4 says not P and Q. So you see this not P right here. We calculated in question 1 that not P is true, right? Because P was false, and you take the opposite of that, which is true. So now you have a true right here, a true, and another true. So Q is true. So you have two trues, so right here. So you have P is true, Q is true. That means P and Q will return true. So that means that for question 4, the answer is also true. All right. Are there any questions about this? France is also in South America? Where'd you get that information, mate? And whatever. It's like the obvious France should be here. Okay. Let's move on to the next slide. Hope you guys have any more questions about this. Let's look at another logical connective. This is also a very important one. It's called we call it if then, just as like slang, I guess. But there's a more formal definition. It's called logical implication, but we can call it if then. So for the if then connective, you can see that it has this arrow symbol. It's P pointing to Q. So P right arrow Q. That's what if then is. And the way you actually read this though is so why it's called if then. It's read as if P then Q. So that's how you read this. Another way you can also read it was P implies Q. Right. So if P then Q or P implies Q, both of them could work. And this is known as logical implication, as more formal term for it. And here is a truth table for the logical implication. So you see we mapped out all the values of P and Q. So they can either be both false, both true, or one false and one true. And here are the subsequent values for if P then Q. We'll call it if P then Q. We usually don't really use P implies Q. So we say if P then Q. I think it's more common in everyday language. So you see some of them are like a bit confusing to figure out. So some of them are pretty obvious though. So say you have two truths. So if P is Q, then Q is true. This will return true. If P is true and Q is false. Sorry, if P is true, Q is false, then if P then Q will return false. But you notice here that for the first two, you see that P, if P then Q, returns true whenever P is false. So it's for these first two possibilities right here. So we have P is both false. So why is that? So why do you think so? Well, we'll look at this in the next slide. But yeah, this is the I guess the most confusing logical connective out of like all of them. So we're going to take a deep look into this. So I'll cover this with an example. So just get you guys understanding like why for each of these values of P and Q, it will return these values of if P then Q. So we'll look at an example. So here's the example that we'll look at. So here's the compound proposition. So look at this. If I study hard for my upcoming test, then I will do well. So you see that this has a structure of if P. Sorry, you see the word if, and you also see the word then after a comma. So you see if P, then Q. And where P is equal to I studied hard for my upcoming test, and Q is equal to I did well. So this part right here, I will do well. We just put it into past tense. So Q equals I did well. So remember, so we have 4 cases of P and Q. So we'll look at each of these individually. So more obvious ones. So we have in case 1, we have P and Q are both true. So if P is true, Q is true, then this, so if P then Q will also be true. This is because like both propositions match what the compound proposition says. So you see that, so you studied hard and you did well, that means that this statement is true, right? So if I study hard for an upcoming test, then I will do well. And so I studied hard for it and I did well for it. That matches with the compound proposition. So it means that if P then Q will return true. Now look at case 2. Case 2 is P is true, but Q is false. So basically, if you want to write this in English terms, is this: I studied hard for my upcoming test, and I did not do well. So false of Q would be I did not do well. Right? So I studied hard for my upcoming test, but I did not do well. This would return false because you're implying that you didn't do well when you studied, even though you studied. So this statement says, if you study, you do well. And then when I did study, I didn't do well. So it means that this statement, it might not make sense in like English terms, but like in mathematical terms, like logical terms, this statement here would return false. Right? Okay, are there any questions so far about this? I know this is a confusing topic. Let me know if you have questions before we move on to the final 2 cases. These are most confusing ones. You have no questions so far? Okay, hopefully you guys are understanding this content. I know it's confusing. Let's move on to case 3 and case 4. So case 3 is where P is false and Q is true. So if P is false, that means I did not study hard for my upcoming test. And if Q is true, that means I did well. So if you combine these together, you say like, I did not study hard for my upcoming test, but I still did well. You can say that. So what would this return? It would actually return true. It's kind of weird why it would return true, but so this returns true. It's because that you can only call the compound proposition, so this proposition right here, you can only make a case for it, like you can only call it false if P is true. You have to satisfy P first before you try to make any assumptions that the compound proposition is false. So remember, P is I study hard for my upcoming test. So if P is false, that means I did not study hard for my upcoming test. So if you did not study hard for your upcoming test, that means you can't make any assumptions about this statement right here. So you don't know if you do well if you study hard for your test, because you didn't study well. If you study well, you can make an assumption about this, but you didn't study well. So you don't know what's going to happen if you actually did study well. So if we say not false basically just means true. Like it might not be true if like you can like not study hard at all and you can still do very well. Like that's also possible, but like in logical mathematical terms, we just say that if this statement we can't prove it that's false, we just call it true. It's kind of weird, but that is what it is. So say here if P is false, you can't prove that the compound proposition right here is false, right? And then for case 4, P is equal to false and Q is equal to false as well. This is the same argument as case 3, where P is false, where the first proposition is false. This is also true. This will also return true. All right. Are there any questions about this slide? Any questions? Please ask away. There are no questions? You guys understand this? All right. Okay, if there are no questions, we're gonna move on. I think there's code problems after this. Next slide. All right, there are problems. Okay, let's look at each of these. Determine if each of the following propositions are true or false. So you have each these 5 propositions. So figure out, so you see that each of them have the structure if, then. So basically the logical implication. So figure out what P is. So there's going to be 2 propositional variables, right? You call them P or Q, but it doesn't matter. So figure out what the first propositional variable is, and then figure out what the second one is. And then you can like reference this truth table to figure out if the whole thing returns true or false. So I'll give you guys a minute or so to do that. All right. wait a couple more seconds. There should be more truths in that, Aiden, I think. Yeah. Should be have too many falses. Yeah. Because you can see in this chart, it has like if you use probability, you say it has like a three-quarters chance of returning true if you set P and Q randomly to true or false. So you see that 3 of the outcomes will return true and 1 of them returns false. So there should be more truths in here. Yeah. Elaine says TTF. Okay. Okay, all of you have some mixed answers, so let's check it out. Okay. So let's look at question number 1. So it says if this slide has the color orange, then this slide has the color blue. So can someone tell me what the first propositional variable should be? Actually, no, I'll just take it out. Oh, go ahead. Yeah. If you see that the word problem is indeed blue. So if you just see colored orange, so you see there's a color orange in the slide. The background is kind of orange, but you can see like there's some shapes right here that are orange. So that means that this first proposition is true. And you see that this slide has the color blue is also true because you see the word problems. This is in a blue font. So that means that, so you have if true, then true. That means that this entire compound proposition will return true. So answer for question 1 is true. Right? What about question number 2? So we have 1 plus 1 is 2. Then 1 times 1 is equal to 2. So the first proposition is 1 plus 1 is equal to 2. Hopefully you guys know that 1 plus 1 is equal to 2. Right? So that's obviously true. The first proposition is true. And then the second proposition says that 1 times 1 is equal to 2. And hopefully you guys know your multiplication tables. You obviously know that 1 times 1 is 1, not 2. So that means that this proposition is false. So we have if true, then false. So we have if, so P would be the first one, Q would be the second one. So if P, then Q. P is true, Q is false. That means that if P, then Q will return false. So answer for question number 2 is false. All right, question number 3. So this is where it starts to get confusing, right? So if the weather outside is snowy right now, then humans can fly. All right. So the first proposition says that the weather outside is snowy, and it's obviously not. It's pretty sunny. So that first proposition right here is false. And that basically automatically means that the whole thing will return true. So if you see that P, the first proposition, is false, that means that if P then Q will always return true. So we don't care about what Q is. But I mean, we could figure out what Q is. So if Q would be equal to humans can fly, obviously they cannot fly. So that means that Q is equal to false. So this is just if false, then false. And that means that question 3, the answer will be true. Okay. Question number 4 right here. It says that if 4 is larger than 5, then 6 is larger than 5. So see that the first proposition says that 4 is larger than 5. That's obviously false. 4 is smaller than 5. So it means that this will automatically return true, this whole statement. And 6 is larger than 5, that is true. So we have if false, then true. So it means that this whole thing will return true. If we follow this truth table right here. And then the final question, this states that if I am older than all of you, so if I am older than all of you, then the earth is flat. So me, I'll just say it's me. Okay. I should have made it more clear. Yeah, okay. I'll just say if Eric. older than the students in this class. All right, hopefully that makes it more clear. Just say it. Sorry about that. So if I am older than all of you in this class, so sorry, should have clarified that. That means that the Earth is flat. If I'm older than all of you, then the Earth is flat. So this first proposition right here, if I am older than all of you, that should obviously be true. So if true, then the Earth is flat. Hopefully you guys know that the Earth is not flat, it's not 2D, it is a 3D. Even though there are people outside this world, even though there are people who think that the Earth is flat still. So don't believe them. Don't be a flat earther. That's what I'd say. So hopefully you guys know that the Earth is a 3D sphere. So please remember that. Right? So this second proposition is false. So we have if true, then false. Or P is true, Q is false. Hopefully you remember that that is equal to false. So it means that answer for question number 5 is false. All right. Are there any questions about this? Any questions about these problems? Okay. We are almost nearing the end of the slideshow. All right, let's move on. So let's look at something called logically equivalent propositions. So what does this mean? This basically means that if multiple propositions are logically equal to each other, that means that they return all the same values for true and false, no matter what the P and Q are. So to prove that two or more propositions are logically equivalent, we will use a truth table to see if the results all match. And below here we have an example of that. So this is an example. Proof that this proposition, so we have not, and then in brackets, this is P and Q. Remember, upside down V represents and, so not P and Q is logically equivalent to not P or not Q. So this has already been proven. This is actually called De Morgan's law. So this equivalence, you can call it an equation if you want, but I guess this is called De Morgan's law. So you see the way we prove this is that we use these truth tables, right? So we get all the possible values of P and Q together, right? So you have P and Q are both false, or they're both true, or either one of them is true and the other is false. So for these two cases. So you can see that if P is false, Q is false. So that means that first you calculate, so for this one, so not in brackets P and Q, you calculate first whatever is inside brackets. So basically you still follow BEDMAS. It's kind of like BEDMAS. You still follow those rules for these propositions. So you have P and Q, so if they're both false, that means P and Q is false. And then you just take the opposite of that, right? Take the opposite of the false right here, and you'll get true. So basically, not in brackets P and Q will turn true for two falses. How about false and true, and what about true and false? So you have false and true, or true and false. Those will both return false. But then if you take the not of that, so you take the opposite of that, that means you'll get out true. So these both are also true. And so you have two trues, that means P and Q will return true. But then the not symbol will make sure that it returns the opposite of true, which is false. So you see that for this table, you have true, 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 false. And you want to see if that matches with whatever this has to, whatever not P or not Q has to return. And then you can see here that if P, I won't go over why these are true and false. You can see that the results match if you figure out in the end. So you see you have true, 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 false over here as well. Same thing with this table. So if you see that these two results match, that means that you notice that this proposition is logically equivalent to this proposition. All right. Are there any questions about this? Any questions? Okay, if there are no questions, let's move on to a problem. So here, prove that this proposition, so not in brackets P or Q, is logically equivalent. So this equal sign, but it has 3 lines. This means logically equivalent to. So prove that this is logically equivalent to this. So not P and not Q. So this was kind of similar to the example in the past slide, except this had and in the brackets, this one is or in the brackets, and this one's and this one was or. Very similar. So prove that these are logically equivalent. I'll just take this up right now. Okay, so let's see if I can create, so bear way to create tables. Or let's just draw these lines. So we have, let's create this table for the first one. So P, Q, right? So P, Q, first one was P, not P or Q. So like that. We also create a second table. Here we'll have P, here we have Q. And then we also have, for the second proposition, we have not P and not Q. So that. And so basically, let's try to, so first let's figure out all possible combinations of P or Q, P plus Q. So, and there's 4 only, right? So we have both of them are true. P is Q, true is false. Sorry, P is true, Q is false. P is false, Q is true. And P and Q are both false. I'll do the same thing for this one. All right, there we go. So those are the possible combinations of P and Q. So let's take a look at what each of these propositions will be equal to them. So we have P is true, Q is true. In the brackets, we have P or Q. So P or Q will return true for us. But then we have the not outside of it. So if we take the opposite of that, this whole thing will actually return false. All right, and we'll do the same for each of these 3 other cases. So P is true, Q is false. True or false, I will return true. And take the opposite of that, you'll get false. So remember that this column right here, so these 2 truths, is just P or Q. And then the final result is this column right here, which is these 2 falses that we have so far. So we have now in this first case, the third case, we have false or true. I'll return true. Take the opposite of that, we'll get false. Finally, we have 2 falses. So false or false will return false. But now we take the opposite of that because of this negation sign. So that will leave us with true. Leave us with true at the end. Right? So that's that for the first table. Let's look at the second table. So the second proposition. So we have true and true. P is true, Q is true. So not P would be false. Not Q would also be false. So not P and not Q. That will return false. So the final result will be in between. So this middle column right here. This is where our final results will be. So next one we have P is true, Q is false. So not P would return false. Not Q is, so not false is true. So false and true. So remember that for and, we need two truths to be true, and otherwise it's false. So this would return false. And let's look at the last two cases. So P is false, not P will return true. Q is true, not Q will return false. So true and false, that would return false. And finally, we have P is false, so that would return true for not P. Q is false, not Q would be true. So we have true and true. So that will return true. And as you can see here, let me use a CBI highlighter, get different ink. So you can see that these results match. So this result, so that's the final result. This is also a final result. So you can see that these results match. So yeah, false, 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 true. Same thing for this one. All right. So that means these two propositions are logically equivalent. All right. Are there any questions about this? Any questions? Okay, if there are no questions, let's go back to the slideshow. I believe there's a couple problems left. All right, so more problems. All right, so here's the first one. Here are a couple of propositions. We have the proposition A. This is, I am eating spiders for dinner tonight. The proposition B is, I am drinking mud water for dinner tonight. And the proposition C is, I am going to be full tonight. Right? And what the question is asking is to represent the proposition, so this compound proposition. So it says, if I am eating spiders and not drinking mud water for dinner tonight, so note the and right here, and also the not right here. If I'm eating spiders and not drinking mud water for dinner tonight, then I will not be full tonight. So represent this proposition using the variables A, B, and C and the logical connectives. So for example, you have the negation sign, you have also the implication sign, so not, if, then, etc. So try to use those symbols to represent this proposition. I'll give you guys a minute to think about that. Yeah, I don't think you'll be able to type this out. Actually, if you want to type this out, like type your answer in the chat, like use the word not for the negation sign. So if you're using this symbol right here, the not symbol, just type not. And if you have and or, like upside down V, or you have normal V, just type and or. And you have if then, I guess you could just type the arrow, or you could do, yeah, just type in the arrow, that'll be fine. If you have an answer. I'll give you guys a minute to think about that. Yeah, Bob, I think you got it. But we'll look at the answer like using the symbols. But yeah, that's the gist of it. So, perfect. Okay, I'll wait a couple more seconds. I'll take it up. Okay, I'm going to take this up. Go to news. Right, make some space for that. Nope. Okay. I guess I'll type out all the things again. So A was equal to. I just say, I'll make it short form. So eating spiders. B was equal to drinking mud water. And obviously don't do this, of course. It's just for fun. So C is equal to, and this is like, I'll be full tonight. Full tonight. Well, that's what the question was asking. And then the proposition was, so I'll just write proposition. If here, if I'm eating spiders and not drinking mud water, then I will not be full. Yeah, so if I'm eating spiders and not drinking mud water for dinner tonight, then I will not be full tonight. So how do we represent this using the symbols and the variables? So the first thing you want to figure out is you want to figure out what the connectives are. So you want to see those key words, so like if then, if you see word and or you see word or, you want to figure out what those are first. So you see there's the first thing that probably come to mind to most of you is you see an if then. So it means you'll obviously have an arrow in here somewhere. So like if you the implication symbol, so you have an arrow somewhere. Not sure if I can, I don't think I type in a proper arrow here. So that's the best I can do. Next thing you notice is that you have an and right here, and you also have a not right here. So with this if statement, so you have an and right here and also a not. So, sorry, okay, let me not type it out. Let's write it out. So you're going to have an arrow using a marker. Whoops. Make the font a little bit smaller. Right. Right, sorry. So you have an arrow right here. So you see there's also an and a not. So you see these two keywords. So we're going to need to include them in here somehow. So let's just put and right here. So remember, upside down V represents an and, or you can call it the caret symbol. Whatever. And not is like a rotated L that looks like this. Right? And you also see there's not right here for the then statement. So the second part of the if then statement. So you see if there's a not, that means there's going to be a not symbol, right? So if you get all this, now you have all the symbols ready. Now let's just fill in the variables, right? So it says here that if I am eating spiders, so just A, right? A is just eating spiders. If I am eating spiders, there's no not in front of that, so we just write A. And it says here, and not drinking mud water. So we see it's not drinking mud water. It's basically just negation B. So we just put B right here. So see A and not B. So if I am eating spiders, so it's A, and not. So these two symbols, and not drinking mud water, which is B. Right? So you see this if then is represented by this arrow right here. And it says, then I will not be full. So be full will just be C. So this is how you represent this proposition using symbols. So A and not B implies not C. So just like that. Right? Are there any questions about this?